Okay, continuing on with homework 4, here's problem 2, where we have the UHart track team. They have some runners that are participating in a meet. And, oh, wait a minute, did this just clear out on me? Double check is still running. Yeah, okay. I saw the little thing blink off around the second monitor. Kind of distracted me. Okay, let's see. Runner A, this dude, is, I assume it's a dude. I don't know. Could be girl. Is going at 4.5 meters per second, whatever that is, in the straightaway here. And so there's a guy, speed is increasing, so this is accelerating at 0.5 meters per second squared. Runner B is rounding the corner right there. By the way, the lane that they're in is at a radius of 45 meters. And they're moving at 5.25 meters per second, but they're decreasing their speed at 0.75 meters per second squared. So they also tell us that this is 20 meters in distance. Oh, by the way, that's a red herring. I don't think we need that information. Before the turn, and runner B is here at 30 degrees, okay, from the road. And we want to find the velocity of B with respect to A, and we want to find the acceleration of B relative to A. So the good thing to do in many of these problems, aside from rewrite down all the givens and the finds and that kind of thing and draw a diagram, is to try to write the vectors for what we know. Okay, so I've actually already written them up here, but let me rewrite them as the velocity of A is 4.5 I, right? Now that gives us direction. It's positive and it's in the I, so we know that right there. So we could also write the acceleration of A. All right, so these are just given, 0.5 and J meters per second, right? So they're, no, not J, that was dumb, I. I don't know what I'm doing. Okay, now let's see what the velocity of B is going to be. Now it's best to probably do this in, I'll write it over here. So these are the coordinates right there, right? So this is the normal. I should probably have done the, and here is the tangential. See? So we're given this right here, and I didn't bother making this a vector. This was just the speed. We know that they're going in this direction right here. And we know that theta is 30 degrees. So I'm going to go ahead and keep that theta as right there, right? That's where my 30 degrees is. I'm going to remind myself. So in terms of VB, it's going to be a positive 5.25 ET meters per second. Remember, velocity is always tangent to the path. So by definition, the speed times the tangential unit vector is the velocity of B, right? The acceleration of B, but now we have to be careful here. We also had, I wrote down that they told us it was decreasing in speed. That's the tangential, and so it's going to be negative. All right, so we also need the normal, right? So let me write the acceleration of B in the normal direction can be found from the velocity of B squared divided by the radius. So 5.25 squared divided by 45. So we would find 5.25, squared, 45 divided. And so we're going to, is it 0.6125? Is that correct? I think I did that right. It's a pretty small number, so I might want to double check it, but I think it's correct, right? And that's in the normal direction. So if we were to write out the acceleration of B completely, it would be a negative 0.75 ET plus 0.6125 EN meters per second squared. Now, here's the dilemma we often have. This guy is traveling in X and Y, and he's traveling in E and T. So we could convert him into the ET and EN. Did I say ENT? I meant the tangential and normal, right? This guy's in the tangential and normal. This guy's in the X and the Y, really X. We could convert him into this coordinate system and then do the math of one subtracted from another to be able to get the relative one. But it's probably better to turn this guy into I and J and then perform this. And most of the time, I think with most problems, it's kind of maybe understood that we want a magnitude and direction. Unless they're asking for it in a particular coordinate system, you should really give a magnitude and a direction and by way of a quadrant, symbol, and an angle, right? And that tells us all the information that we would want to know. All right, so we'll once again create a coordinate transformation array. Start out with the X and the Y. It's a good place to start. So here's your I and here's your J. And now our tangential is, remember that the normal was coming at 30 degrees right there, right? So the normal was, I'll even extend this thing a little. Sometimes I wait to extend it, but I'll extend these a little bit. We know that this was pointing down that way right there. So here was your EN. And then our tangential one, perpendicular to that, was down this way. So there's your ET. So I don't think that's that much different from the previous one. No, like I said, the previous problem, we were coming this way. So we'll have like a slightly different thing. And the angle, the easiest one to use, if we see this was already this way, we know it equals this. So we'll call that, we'll keep using that as theta. And as I've mentioned before, sometimes this helps to extend these axes. And it really does help to have one of the angles significantly smaller than the other. If you start getting in, this thing starts getting like 45 degrees, and you'll see that, by the way, in lots of different problems where you can have some a little bit, make it a little bit more difficult if you draw the thing as if it's like close to 45. If you can really kind of exaggerate where there's acute, one angle is very much acute and the other is a little bit larger. That makes it better. Okay, so the coordination transformation array. Let's see. I'll make my little box thing here. Try to make it neat. I don't want to go. I don't need to go crazy with it, but we'll go 2 of these lines deep here. 2 lines deep. There's that looks pretty good. All right. So we'll come up here and then there. Yeah. Yeah. Okay. I made it pretty neat, I think. I think so. And I'm going to do my I here and my J. You could do it the other way around, by the way. You could do the I and the J here and the ET and the EN up there. I just think, make it a consistent. Don't have to worry about it. All right, so let's take a look and see what ET is with respect to I. Well, it's going to be positive, and it's going to be the sine of theta. All right, because that's the opposite. That's ET has some of there going. So sine of theta. Let's see how much in the J. Oh, it's going to be the negative. So it's going to be negative cosine of theta. Take a look at the EN now with respect to I. EN is in the negative I direction, and it's going to be the cosine. So negative cosine theta. And it makes sense that they're opposite from each other. This should be sine, and we're predicting that it should be negative as well, because only one of them can be positive, or the other way around, only one of them is negative, right? So 3 of them are one way and one of them is the other. So let's look here. The EN, sure enough, is going in the negative J direction, and it's going to be sine, so as predicted. Now we do the velocity. We have to convert this guy into I and J, right? So the velocity of B is going to be equal to 5.25 times the sine of 30 degrees I plus 5.25 times negative, so I'll put a there, cosine of 30 j. So I might be able to squeeze this in right there. I got that right? Yeah, yep, okay. 5.25 times 30 times the sine times, so 2.625 I plus, and this is going to be a negative number, just got to remember that, 5.25 times the cosine, so we're going to get a negative 4.547 J. And these are meters per second, so I almost fit it within the margin. Okay, so let's turn the acceleration at B. I might be able to fit everything onto this one page, so I'm going to go up just a little tiny bit. I tell you not to scrunch it, and I think it's a good idea, but I would like to keep everything on one page if possible. Okay, so we'll take this and turn it into I, and we'll take that and turn that into I, and take this and turn it into part of the J, and turn that into part of the J. Okay, so that's our plan. So I'm going to go brackets first, and I'll take my negative 0.75 and multiply it by my sine of 30 plus, now I'm going to take this part right here and I'm going to multiply it by that. So 0.6125 times a negative cosine of 30, and that's going to be I. Alright, so we do the same thing for J. We'll take this, multiply it by that, negative 0.75 times our negative cosine, so it's a negative times a negative, I'll watch out for that. And then we're going to add in this part times this to get that part of the J. So 0.6125 times the negative sine of 30. Close, 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 close. Okay. Yeah. So the acceleration of B is going to be equal to 0.7530 sine times, I do that. That's going to be negative, I'll remind myself. And then 0.6125 30 cosine times, and that's a negative, so let's track that out. Negative 0.9054 I plus, so we have negative negative, so it's going to be positive 30 cosine times, okay, so there's there, and then 0.6125 30 sine times, but this is positive, this part, but this is negative, so we're going to subtract that out. We still end up with a positive value of 0.3433 yeah, J. And these are meters per second squared. Okay, so now we have this in I and J, and we have this in I and J. We have this is an I, and this is an I. So if we want to get the velocity of B with respect to A, we subtract out A from B. So B is this guy right here. So 2.6125, and A is up here, so we're going to minus this out, minus 4.5, that's going to be I, plus, And now there's nothing in the j direction here, so this right here is just equal to that. Negative 4.547 j. So can I fit it in? I think I can. We'll get 2.6125, 4.5, subtract it out, it's going to be a negative 1.888. I should not try to squeeze this in there. It just won't fit. Try it. And then this part, negative 4.547 j meters per second. It didn't fit. Okay, but a good thing to do in the answer is to find the magnitude. So I'll take the square root of those two. And by the way, it's down in that lower left-hand coordinate quadrant. That's what I meant. You know what I meant, right? Squared plus my 4.547 squared. So let's see, that's already in my calculator. I can square that in the 4.547 squared plus square root. Okay, so I'm gonna double check this number. It seemed kind of big. Nope, that makes sense. Okay. So we end up with 4.923 meters per second. And let's look at the, I never know what kind of subscript I want to put onto this angle right here. I could call it B with respect to A, or I could call it VB with respect to A. That's a lot of subscripting. Inverse tan, and we're just going to go rise over run. Don't worry about the negatives, because they'll take care of themselves. By way of, because we already know what quadrant, just from observation we know what quadrant it's going to be in, so we just want what the angle is going to be, and then we can pair that up with the quadrant. 4.547, 1.888, divide and take the inverse tangent. We get a 67.45. 67.45 degrees. All right. Do a similar thing. So I'm going to move my stupid keyboard out of the way so I can move my. All right, cool. I just burped into my breath. That's gross. All right, so now we want to get the acceleration of B with respect to A. So we get the acceleration of B with respect to A. And so we start out with B, the acceleration of B, which we got is this right here. Negative 0.9054, right? But we're subtracting out A, which we knew up here is a negative, is going to be minus 0.5. So it's going to be minus 0.5, and we know that's going to be the I direction. And this has nothing in the J direction, so this is just B. I should have written this out. Darn. I should have written out what we were doing. Not a good idea to just start jumping into something. Should really rate what the thing is. So I'll have to repeat that, sorry. So this is the acceleration of B minus the acceleration of A. All right. And so we'll take B, which we said was negative 0.9054, and then minus that 0.5, and that's the I, and then plus, and that's just going to be this guy right here, right? Because there's nothing to subtract out in the J direction. So that's not anywhere in there. Stack, no, it's not. So I'll have to 0.9054, 0.5 minus, so it's going to be plus, we have a negative 1.405 I plus 0.3433 J meters per second squared. All right, so there's that answer there, but it's best to, once again, get the magnitude and direction of this thing. So that's going to be the square root of negative 1.405. I don't always put the negative inside there because why bother? It's getting squared, right? 0.3433 squared. So do I have those both in there? I do, don't I? Okay. So that ends up being not too much from 1.447 meters per second squared. And then we call this theta, I call it A, B with respect to A. Not that it matters, I know what I mean. So I get the rise 0.3433 over 1.405 0.3433 and 1.405 and divide and then take the inverse tan, and that's only 13.73 degrees. And we note that this is in the downward direction, but the going to the left but up, right? So that's in the second quadrant. So if I go answers, I can say A is going to be velocity of B with respect to A is equal to, so it always happens at the 20-minute mark. Velocity of B with respect to A is going to be 4.92 meters per second, and what did I say? It's going to be in this quadrant at 67.5 degrees. Ah, I made that too big. Let's see. I'm gonna squeeze it a little bit more. Shh. I should have. There you go. Squeeze that, and 67.5 degrees, and then B, the acceleration of B with respect to A, and 1.45 meters per second squared. And what did I say that was going to be? It's in the negative x direction but positive, so this one right there, that quadrant, 13.7 degrees, and I got it to fit. Whew. And let me box this out. It's almost just better to just use more paper, spread it out some more. There's no real benefit because you could just buy some more paper. It's not that big of a deal. It's pretty cheap per page, really, if you think about it. And if you have some left over, what a waste. So there you go. That's problem 2 in homework 4. Now we'll go to problem 3.